Hello everyone, welcome to a tutorial on LL1 grammar. Today we are going to look at an example from our notes. You can find the example in section 4.8 and on page 51. We're going to take this example and we will check whether this grammar is an LL1 grammar or not. Okay, so let's get started. This is the example from the notes. This actually defines this is actually the grammar for your F program that you're familiar with from labs 3 and 4. And so let's just take a deeper look at this grammar. So this grammar, first of all, is in eBNF that you can understand by looking at the special symbols that are actually from regular expression. So the star means that you repeat it 0 or more times, and the bar means that it's or. Okay. What else does this grammar have? Of course, all the letters with uppercase first letters are non-terminal. So program, formula, var, they are all non-terminals. And everything else is a terminal. So this is the end of file indicator. This just means that we have finished parsing. It's a terminal. It's a special terminal symbol to denote that that is the end of the file. We have semicolons. We have opening brackets and closing brackets. We have the not. We have 0 or 1, and we have ID. So just think of ID as any sequence of terminating characters. Okay, that is. I'm sorry, I'm just going to delete all this. Okay, so that is our grammar. Clearly, you can see that this generates the kind of F programs that we want, right? Sorry. Okay. I think I'm done erasing stuff. Right. So just take a moment to convince yourself that this generates all the F programs that we want. Okay. Now, in order to check whether this grammar is LL1, the first thing you have to do is you have to get rid of these fancy star symbols and make this grammar into an actual BNF form. Okay, so we need to convert eBNF to BNF. The way we do that is we take these star operations and introduce a new non-terminal that encodes them. Okay, so let's take the first production rule, which is program goes to formula star and end of file. Okay. To convert this, you first take the thing that has to be repeated 0 or more times and you name it into a non-terminal. So let's call it flist. So instead of 0 or more repetitions, I'll just call this flist. Okay. And now flist has to simulate the star. So flist can go to epsilon. This means it's repeated. It's not repeated any number of times. Or it can go to a formula and then another flist. Okay. So this denotes the one or more repetition. So just convince yourself that this thing is equivalent to these three set of rules. Okay, so this is how you would convert a rule that has a star into BNF form. That was the first rule. Now the second rule was formula to var equals, so var assigned expression. Let me just make sure that was the next rule. Yep. Okay. So this rule is already in BNF. We don't have to do anything. And now we have expert goes to term star, or not term star, it's term and then oops, the whole group star, right? Let me use a different color. So this whole group repeated 0 or more times. Okay. So this again, now to encode star, we just use a new non-terminal. So let's call it term tail. So let's call it term small tail. Okay, so term tail can go to the empty string, or term tail can go to plus term and then term tail again. Okay. So this will simulate the infinite repetition. And now term goes to factor, and so this was factor and dot factor star. So we once again introduce a new non-terminal, factor tail, and factor tail goes to epsilon, and factor tail goes to dot factor and factor tail again. Okay, so we have taken care of all the stars. Now we just have to split the ORs. Again, in BNF, you cannot have these ORs, so you'd have to simply split them into multiple rules. That would be factor is not factor. Factor can go to expert and then closing bracket. Factor can go to var. Factor can go const. Var can go to ID. These are already in BNF. Const is 0 or 1. We cannot write that in a single rule. We have to split that into 2 rules. Okay, so converting a eBNF to BNF gives us a much larger grammar, right? This looks way bigger than the earlier one. Now we are going to have to use this as a reference. So I'm just going to split my screen here. There's a previous tutorial. Okay, so this is what we just wrote. I hope this is reasonably clear. Okay. Good. Yeah, I can't make this any bigger. Okay, so this hopefully is reasonably clear. This is the reference grammar. This is the BNF grammar that we generated. And now the question is, okay, how do you determine whether this BNF grammar is LL1 or not? Okay, so LL1 has to do with left look ahead 1. When parsing, you only have to look ahead 1 token in order to identify which rule to apply here. Okay. So let's try to understand what that means before we actually do the test for LL1. So let's just try to write an F program. Okay, so this is a sample F program, right? So this is a program with just one statement. and we should be able to parse this. So let's try to intuitively write how we would parse this. So you obviously have to start with the first rule, which is program goes to flist and end of file. Of course, we had to write the end of file here. And now the rule that you would apply is that you would expand this flist. And I'm going to show that using a double arrow. The rule that you would apply is you take flist and you convert that into formula and flist. So now the string that you will have is formula, flist, and a file. Okay, and this is called a derivation. That is, you start from the start symbol, you apply many rules until you get the string that you want to parse. Okay, so the technical name for what we are doing is a derivation, and it is basically a fancy name for parsing. Derivation is like parsing. It's not the same as parsing, but just like parsing. Anyway, if you want to derive this string, what you would do is you would change, you would apply the rule for formula, and formula should go to var expr, right? So now you got var expr. You still have the remaining flist and a file. And then var, you can go make that into ID. So you got ID expr semicolon flist and dollar. And the next rule I'm going to use would be expr to term and term tail. What would that look like? That would be term, tail, semicolon, flist, $. Okay. And just to, I think this is enough. You can derive further. You go from term to factors, factor to var, and that's how you would derive this. So now ID is already A. So we are not going to, so ID we consider it as a terminal symbol. So for now, just imagine that ID is a placeholder for any variable. Okay. So ID is already A. So we have derived A. We have derived parts of a string. Namely, we have derived A less than A signs something semicolon. And if you apply the rule for flist, so let's just do that too. Now I'm going to just arbitrarily use a rule which says flist goes to epsilon, our second rule. And that would be term, then you got term tail and dollar, right? Since we just removed flist. Okay, so this is what you would get. So we have derived part of a string, right? We have derived A less than nothing and the end. So this should somehow, after many applications of our rules, this should give us B plus C. That's the idea. Now, the question is, how do you do this automatically? Here we did it using our intuition. And what we would like to do is we would like to code up this intuition, and we would like to code it up as efficiently as possible. Why did I apply this set of rules? Because I knew that I wanted to derive A. Okay? And this is the basic intuition. this is what a parser should do, right? So it should just look at the string and then come up with the set of derivation rules. And LL1 is a class of is a grammar such that you can design a parser in which you only have to look at the first token and you can decide which rule to apply. So which of these rules to apply. Okay, so I'm not going to explain how the parser works, but I'm just trying to give you an intuition of what we are computing. Okay? We are computing three things called epsilon set, first set, follow set. Okay, four things, and a predict set. The first set intuitively says that what are the things non-terminals can go to. Okay, for example, here when you apply var this rule, we replaced our non-terminal var with a terminal ID. So the first set for var should include ID. Okay. And what else? So first set just says that whenever you replace a non-terminal with a terminal, what is the first element of that terminal? And you have to give out all of that. Okay. I wanted to give a deeper example. So let's try that. You got program and you got flist and dollar, and you know that flist can just go to epsilon. Okay. Then if you just apply these two rules, it looks like program is just going to give you this terminal. Okay, so if you apply these two rules consecutively, you will get this following derivation. So now the special symbol should also belong to the first set of program, because in your derivation, you were able to derive $$ as the first element of a string that is derived from program. Okay, so first set would be what are the first first terminals that you can derive from the non-terminal. Okay, I didn't explain epsilon because that's easy. Epsilon is the set of all non-terminals that can go to the empty string. Now the third thing that we need is the follow set. Now the follow set just says that what are the things in a derivation that can follow a non-terminal. For example, in our derivation, let me just use different color. Okay, so in our derivation, we generated this intermediate string, right? The intermediate string is way bigger than what I've drawn. This intermediate string. And in this intermediate string, the semicolon followed expert. Okay, so the semicolon would be in the follow set of expert. Similarly, if you when you expanded expert using this rule, then the semicolon followed this non-terminal, term tail. So the semicolon is in the follow set of term tail as well. Okay, and similarly, the $$ would be in the follow set of flist. Okay. We'll need to keep track of this. Now, why do we need to keep track of it? Well, it's because we need to keep track of this because when you are parsing it, we need to understand how to get rid of stuff. Let me try to explain this better. just remove what I have written. Oops. Okay, I was trying to explain why we need to compute the follow set. When you're passing it, you need to know that, for example, let's say you passed A and you're at this state. Just before you're doing this. Okay, sorry. I had to go offline and think really hard about how to clarify this. I think I've gotten a good idea about how to clarify it. Okay, so the question is that how would you, why do you need to compute follow sets? And the answer is that intuitively, what I want to say is that, let's say you're passing this string. Oops. Let's say you're passing this string and you reach kind of at this point. Okay? So you have consumed everything, and the next thing that you're going to consume is the dollar sign. Okay, and you have in your parse tree, that is in your derivation, you got something like this, a bunch of strings and flist and something else on the right hand side. Now, you can be sure that you need to eliminate this, right? So the derivation stops once you remove all the non-terminals, and you need to know whether it is possible for you to remove this flist. Okay, and since $$ is the next thing that you want to consume, and if you know that $$ can actually follow flist, so when I say that $$ is in the follow set of flist, what that means is that I can somehow remove flist in such a way that $$ is going to come up next in the derivation. Okay. Hopefully that is clear. If it's not clear, as we do examples, it will become clear. It's difficult to convey that intuition. Anyway, so these are all intuitions of what the first sets and follow sets are. From these two sets, we can compute the predict set. So let's just go into the actual algorithm and not dwell around intuition. So the first set that we want to compute is the epsilon set. So epsilon is a set of all non-terminals that can go to null. Okay. So on the right hand side, you have the grammar. We go rule by rule and check whether non-terminals can go to null. Is program nullable? No, because it has this terminal on the right hand side. Is flist nullable? Absolutely, because flist, there is a rule that directly takes flist to null. Oops, to a bit of here, that's a problem. Okay. What else is there? Flist is nullable. Now the next non-terminal is formula. It's not nullable because the only rule in which you have formula, you have the less than or equal to and semicolon on the right hand side. You have expr. Now, is expr nullable? Well, it depends on whether term and term tail are nullable. Okay, so we'll have to analyze that first. The trick here is to analyze from the bottom because that's much easier than analyzing from the top. So let's just start analyzing from the bottom. Is const nullable? No, because all the rules that have const go to terminal. Oops, let me just select a color. Yeah, all the rules that have const have terminals on the right hand side, namely these two rules. Is var nullable? No, the only rule that has var goes to id, so not nullable. Factor, well, factor goes to const, which is not nullable. Var not nullable. On these two, for these two rules, these two production rules, you have a terminal on the right hand side. So factor is also not nullable. Then there is factor tail. There is a rule for factor tail to go to null. So flist factor tail are both nullable. Is term nullable? Term goes to factor tail. It doesn't look like that's nullable because factor is not nullable. Then there is term tail. So term tail is definitely nullable. Okay. What else? Then we got expr. Expr goes to term and term tail. And as we saw earlier, term is not nullable. So expr is also not nullable. Okay, so that's with epsilon set, the set of all non-terminals that can go to null. Okay, now the next set we want to compute is the first set. Okay, so just as with the epsilon set, it is easier to go bottom up for the first set. So what is first set? As I explained earlier, if you take a non-terminal, what is the first element in the terminal string that can replace this non-terminal in our derivation tree? Okay, so let's take const. So const can directly go to 0 or 1, right? That's easy. Var can, so C should be uppercase, V should be uppercase, or can just be ID. Factor. What are the first things in factor? Well, there is the not, there is the open brackets, then there is var and const. And we know that var can go to ID and const can go to 0, 1. So I'm just looking at these 4 rules and I'm saying that these are the only possibilities for factor, for the first set of factor. Okay, okay, good. And now we have factor tail. Okay, so what all can factor tail go to? There is the dot on this rule. You look at that rule, you replace factor tail with a dot and then something else. Okay, so the first thing will be a dot. And this rule just says there is an epsilon. And those are the only two rules for factor tail. Okay, so this is done. And what is next? Next is term. So term goes to factor, right? So the first set of term is going to be the first set of factor. And since there are no other rules for term, these are the only possibilities. Next thing is term tail. So what are the options we have for term tail? We got these 2 rules. Okay, so in the first rule, it just goes to the empty string. The second rule, it starts with a plus. So the first set would be just a plus. We got expr. Expr is term and term tail. So expr goes to the term. So the first set of expr is going to be the same as the first set of term, which is this thing, open brackets, ID 0, 1. And then you have formula. So formula just goes to var. Var is just ID. Then there is flist. I think we calculated flist. No, we did not. Flist. Flist is these two things. So first set of flist is just the ID, because the first set of formula is just the ID. And for program, what would be the first set? Well, it would be the first set of flist, which is ID. And since flist is nullable, we have to have this as well, right? Because since flist is nullable, program can directly go to $. Okay, let me just double check this. So you got factor. The only rules for factor was $factor. Okay, so factor is right. Factor tail, I think, is right. Term is, so when you calculate the first list for term, you calculate the first list of factor. Since factor is not nullable, we don't have to look at anything else. Similarly, term tail is okay. Term is not nullable, so we for expert also it is fine. Okay, so this looks right to me. Okay, so that's it with the computation of first set. It's really easy. Just look at the left hand for each non-terminal. You look at all the rules where you have that non-terminal on the left hand side. You look at the first terminal that can be derived using the right hand side. Okay. The only thing you have to be careful of is if the first element in the right hand side is a non-terminal, and that can go to null. If that can go to null, then you apply that relation and then try to come up with the first set of the next non-terminal that you see. Okay, so that's it with the first set. The next is the follow set. Computing the follow set is a little bit trickier. So for the follow set, you have to look at when the non-terminal appears on the right-hand side. So as I mentioned earlier, the definition of follow set is that what are the terminals that can follow this non-terminal in a derivation. Okay. So in order for something to be followed, you have to have the non-terminal on the right-hand side. So for the program non-terminal, doesn't appear on the right-hand side of any of the rules. So its follow set is empty. I shouldn't write empty like this. Maybe it's better to just, okay. This is just the empty list, empty set. Now for the flist. You have the first rule in which flist appears on the right-hand side. It is followed by $. You have third rule in which flist appears on the right. Okay, I think that those are only two rules. Now what happens when flist appears on the right? So let me just add $, to a follow set. So we take this, and now from this, can you gather what follows flist? Well, if you look at any derivation tree, whatever follows this flist will be whatever follows this flist. So basically that is a recursive argument, which we are never going to get to the end of. So we can safely ignore that rule. That rule is not going to add any new terminals to our follow set. So the follow set for F list would be $. Okay, what was the next thing? F list, and the next thing was formula. Formula appears here. And I guess that's the only place in which formula appears on the right-hand side. Okay. So what can follow formula? Well, the first set of F list can follow formula, right? So what is the first set of F list? It's just ID. Okay, and then is F list nullable? Well, yes, it is nullable, right? So then if you look at this rule, what can happen is that this F list can go to null, and then this F list can be followed by some terminals, right? Which means that formula can be followed by those terminals as well. So you have to take into account all the terminals in the follow set of F list. So the follow set of formula was the first set of F list, union the follow set of F list. Okay, both are F list, first set and the follow set, just because F list is null. Okay. What is the next one? The next one is expert. So in this rule, expert is followed by a semicolon. In this rule, expert is followed by a closing bracket. Is there any other rule in which expert appears on the right? I don't think so. So it should be semicolon and a closing bracket. Okay. What else? Then there is term tail. Term tail appears on the right several times. Here, okay, just 2 times. Okay, so here term tail can be followed by anything that expert is followed by. So it's semicolon and closing brackets. Here, this rule you can just ignore because we don't get any new information by following that recursion. Okay, now the next thing is the follow set of term. Where is term on the right hand side? These 2 rules. So from this rule, we know that everything on the first set of term tail should be in the follow set of term. Okay, so on this. So first set of term tail, it is just plus. But since term tail can just go to null, whatever follows expert also follows term, which means that you can have semicolon and closing bracket after term. Once again, since term tail can go to epsilon, whatever follows expert can just follow term. What is next? Next is factor tail, I guess. Factor tail appears in 2 places, here and here. Once again, if you look at this rule, whatever follows term can also follow factor tail. So that is these three things. And there is no point in looking at the other rule because it is factor tail goes to factor tail. Okay. This next is factor. Factor appears here, factor appears here, and that's it. Okay. From this application, you can see that the first set of factor tail is going to affect factor. It is the first set of factor tail. It's just the dot. So dot can follow factor. Now factor tail can go to the empty string, which means that the follow set of factor tail is also the follow set, is a subset of the follow set of factor. So dot plus semicolon and closing brackets. And there is no point in looking at this rule because it's recursive. Okay, that is good. The next thing, oh, okay. After factor, we got var. What can follow var? Well, according to this rule, whatever follows factor can follow var. So this plus semicolon closing brackets. Similarly for const, it's the same as for factor. Okay, I think we are done here. This would be the computation of follow sets. And now we compute what is called the predict set. So the predict set is for rules, not for non-terminals. So the first and follow was for the non-terminals. Predict is how do you use these two sets to determine which rule is applicable when. Okay, so I'm going to just write down this rule. Program goes to flist $. And when is this rule applicable? Well, so let me just try to demonstrate that using an example. So this is one of the strings we had earlier, and we are trying to parse it. So let's say we are looking at this. So this is ID. So if you want to apply this rule as you are parsing this, I will only apply it if ID is in the first set of flist, right? So then I know that if I apply this rule, I'll get a string flist $. And from this flist $, eventually, if ID is in the first set of flist, eventually I will be able to derive ID. This is not a requirement. It is just that it is possible that I can derive A from flist. So if I see A, it is possible that I can apply this rule. So that's what the predict set means. So predict set is the set of all tokens such that it allows you to apply this rule. Okay, so if I apply this rule, eventually I will get that. I will be able to consume that token. Okay, so that is computed by computing the first set of whatever is on the right-hand side. And if that thing on the right-hand side is nullable, then you compute the follow set of the non-terminal on the left-hand side. So here the first set of flist is ID. And it is the right-hand side as a whole is not nullable. So this is the only time in which I'm going to apply this rule. Next rule is flist to epsilon. When do you apply this rule? Well, the first set of the right-hand side is nothing. because it's just the token empty string. So we just look at the follow set of flist. The follow set of flist is $. So you only apply this rule when you see the end of it, which makes sense, right? Now you got the next rule is flist to formula flist. When do you apply this? Well, I apply this whenever I see any element in the first set of formula. First set of formula was just ID. Is formula nullable? No. So that's the only time I can apply this. Then formula to var expert. And do you apply this? Well, I only apply it in the when I see the first set of var. Now the next rule is expert term tail. Once again, it is just since term is not nullable, I just look at the first set of term, which is this whole stuff. Just double checking that term is not nullable. It is not. Term tail to epsilon. The first set of epsilon is empty. The follow set of term tail is semicolon and closing bracket. Right. So since the right hand side is nullable, we look at the follow set of the left hand side. Now the other rule for term tail, just term tail goes to plus term tail. That is easy. The first set of the right hand side is just the plus, because that's the first terminal that can appear there. Now we look on the next rule, which is for term, which is factor and factor tail. This would be the first set for factor. That I think was the same as the first set for term. And factor is not nullable, so that's the only possibility here. Next thing is factor tail goes to epsilon. No, this is obviously the follow set of factor tail. What is the follow set of factor tail? It is these three things. Okay, so my iPad is not letting me be lazy. So the follow set of factor tail was plus semicolon closing bracket. Plus semicolon and closing bracket. Okay, the next thing is factor tail goes to dot factor something. Here, the first set of the right hand side is just the dot. I think for all the other things, it's very straightforward. All the other rules, it's just the first sets are easy to compute because they all start with a terminal. Factor goes to expert. There's just the opening brackets. Factor to var is just ID. Just ID factor to const is the first set of const, which is 0 and 1. And var2 ID is just ID. And you get the idea, right? So const to 0 is 0. And const to 1 is 1. Okay, so we have computed the predict sets. Now, before we actually start parsing, we have to make sure that this is LL1, and only then can we actually use just one token of look ahead. And to confirm that this grammar is indeed LL1, we look at all the predict set. We give special attention to rules who have the same non-terminal on the left-hand side. For example, these two rules. These two rules. So these two rules map flist to two different right-hand sides, and their predict sets are different. So that is good. It's not that they're different, it is that they're disjoint. They don't have any tokens, they don't have any terminals in common. For formula, there is only one one rule, so we are good. For expression, we only have one rule, good. For term tail, we got two rules, but the predict sets are different. They are disjoint. Then you got term, only one rule. Factor tail, you got two rules. But once again, the predict sets are disjoint. For factor, you got multiple rules, but for each rule, the predict sets are disjoint. None of them share common elements. And for const, once again, none of them share common elements. So because all these predict sets are disjoint, we can confirm that our grammar is indeed LL1. Okay, to conclude, we looked at converting, we started with a EBNF grammar. We want to check whether it is parsable by LL1. Sorry, we wanted to check whether it is an LL1 grammar. That is, it can be parsed by just having one token of look ahead. The first thing that we did was we converted that into a much bigger grammar, BNF grammar. And then we went over what a derivation looks like to get an intuition of what first sets and follow sets are and why we need them. Then we looked at the epsilon set, which is a set of all non-terminals that derive null, the empty string. The first sets, the follow sets, and the predict sets. And then we concluded that since most the predict sets are disjoint for common non-terminals, our grammar is indeed LL1. Thank you for listening.